Okay, let's unpack this. When you look at a massive modern data center, it's incredibly easy to just see blinking lights, right?
Yeah.
Just endless racks of black boxes.
Oh, totally. It feels monolithic.
Yeah, exactly, like this impenetrable fortress. But the moment an application slows down, or, I don't know, a database hangs, you realize it's not a fortress at all. It's this highly sensitive living ecosystem. And diagnosing a problem in there, man, it could be like trying to find a single clogged pipe in the entire water system of New York City.
It really requires a completely different kind of X-ray vision. I mean, you can't just look at the outside of the boxes. You have to understand the invisible rivers of data flowing between them, the protocols governing that traffic, and the compute engines driving it all at the microsecond level.
Which brings us to our mission today. We are taking a comprehensive, question-by-question journey through the key technical concepts and assessment criteria for the HPE0-J82 exam.
Right, the storage architect exam.
Exactly. So whether you are cramming for the exam tomorrow, or you just want a masterclass in how modern enterprise storage environments behave under extreme pressure, this deep dive is going to map it all out for you.
And just to ground everyone, let's lay out the basic facts of the exam itself. It is a proctored exam, lasts about an hour and 30 minutes. You're looking at 60 questions, delivered in English, and you need a 63% score to pass.
Good to know. And we are going to look at 10 real-world practice questions from the sources. I'll read the full text of the questions and the options, and we'll break down A, B, C, and D for each to reveal the underlying logic. Because out in the field, you aren't handed multiple choice options.
No, definitely not. You're handed a symptom. And you have to trace it back through the hypervisor, the fabric, the storage controller, right down to the media itself.
Right. So before you can master complex architectures, you really need to understand how to control data flow, right? And how to move it safely. So let's start with question 1. Here's the full text.
Go for it.
A customer has a highly transactional database experiencing unpredictable latency spikes due to other workloads on the shared array. Which storage capability is most critical to resolve this issue? Option A, implementing quality of service. Option B, increasing sequential throughput. Option C, adding raw capacity. Option D, enabling asynchronous replication.
Okay, this is a classic noisy neighbor scenario.
Yeah, it's like a busy highway without a carpool lane, right? Some workloads are just noisy neighbors causing massive traffic jams. But my immediate instinct, and I think a lot of admins feel this way, is to just throw more hardware at the problem. So why is C, adding raw capacity, incorrect?
Well, throwing raw capacity, or even option B, sequential throughput at a transactional latency problem, just fundamentally misunderstands the physics of the workload. I mean, a transactional database isn't moving massive, continuous blocks of data like, say, a video rendering farm.
Right, it's doing tiny reads and writes.
Exactly. Thousands of rapid-fire reads and writes. So if you have latency spikes, it means other rogue workloads on that shared array are suddenly hogging the controller's queue depth. The storage brain is overwhelmed. It's not out of space.
So building a bigger parking lot doesn't solve a traffic jam on the highway.
No, you need a traffic cop, which is why A, quality of service, or QoS, is the correct answer. It directly manages I/O behavior. You can cap the IOPS or bandwidth of those rogue workloads like a background backup job, so your mission-critical database always has guaranteed lane access.
Got it. And what about D, asynchronous replication?
A complete distractor. Replication copies data for disaster recovery. It does absolutely nothing to prioritize live workloads or manage sudden bursts of I/O.
Makes total sense. Okay, seamlessly transitioning to question 2. This is about physical deployments. Here's the text. You are planning a non-disruptive data migration to a new HPE Alletra system. Which of the following is the most critical step to ensure continuous application availability during the transition?
Important one.
Right. Option A, verifying the physical dimensions of the rack. Option B, verifying host operating system versions and multipathing software. Option C, calculating the thermal output of the new array. Option D, reviewing the purchase invoices for the legacy hardware. Now wait, shouldn't we care about the hardware specs of the old array? Like the physical dimensions or power?
Well, sure. For standard data center logistics, you care about physical dimensions and thermal output options A and C. And I guess you need invoices for accounting. But the key phrase in the question is non-disruptive. For non-disruptive migration, the physical hardware logistics aren't the single point of failure. It is the logical connection at the host layer.
Keeping the data flowing while you swap out the backend.
Exactly. You have to hyper-focus on option B, verifying host OS versions and multipathing software. That is the correct choice.
Because if the host driver panics when it sees the new Alletra storage target,
your migration is dead in the water. The multipathing software maintains the illusion of a single continuous drive to the application, even as the actual data pathways are shifting from the old legacy array to the new Electra. If that software stack isn't verified and supported, the moment you transition the active path, the host loses access to its disks.
Wow, so the database crashes and it's suddenly very disruptive.
Highly disruptive. So A, C, and D are just logistical distractors. B is what keeps you online.
Okay, so once the data is moved and flowing smoothly, the next big question is really how the business actually pays for and manages that infrastructure. Which brings us to question 3. A customer wants the agility and pay-per-use financial model of the public cloud, but strict compliance regulations require their data to remain on premises. Which solution best addresses this requirement?
This is such a common dilemma right now.
Oh yeah. Option A, a traditional capital expenditure hardware purchase. Option B, leasing used hardware. Option C, a full migration to a hyperscale public cloud. Option D, HPE GreenLake for block storage. Here's where it gets really interesting, It's like wanting the flexibility of a rental car, but insisting on keeping it locked in your own personal garage.
That is the perfect analogy. It's the defining struggle of modern IT finance. The old capital expenditure model, option A, gives you the compliance because the gear's in your data center, but zero agility.
Right. You own the hardware whether it's empty or full.
Exactly. And option B, leasing used hardware, is just a cheaper CapEx model. It still doesn't meter your actual usage dynamically. Then you look at option C, a full hyperscale public cloud migration.
That gives you the pay-per-use agility.
It does, but it immediately fails the compliance requirement of the question. You can't legally move the data offsite, which leaves option D, HPE GreenLake, for block storage. It's the correct answer because it delivers storage as a service directly on-prem.
It changes the financial telemetry rather than the physical location.
Spot on. The physical hardware sits locked in your secure data center, keeping the auditors happy. But secure telemetry monitors exactly how many gigabytes you are actively provisioning and you're billed on that usage.
Brilliant. Okay, moving to question 4. A business is looking for a service offering that provides a designated expert for proactive, long-term strategic IT alignment rather than just reactive support. Which service should you recommend? Option A, next business day hardware replacement. Option B, access to a self-service knowledge base. Option C, a one-time installation service. Option D, HPE Complete Care Service.
This is about shifting operational models.
But wait, isn't standard IT support enough? Why do we need a designated expert? If a drive fails, I call support, they send a drive.
What's fascinating here is the difference between reactive and proactive support. Standard IT support, like option A, next business day replacement, is purely reactive. You are waiting for the ship to hit the iceberg before you do anything.
Oh, that makes sense. The damage is already done.
Right. Same with option B, a self-service knowledge base. You're still fixing something that's already broken. And option C, a one-time install, offers no long-term value at all. The question specifically asks for proactive, long-term strategic alignment.
So that leaves D.
Yes, D is the only correct answer. HPE Complete Care Service brings a designated expert into the loop who actually understands your specific telemetry. They analyze your growth trends and lifecycle planning before things become critical alerts.
So they're looking ahead, not just swapping out dead drives. Okay, we covered the business side. Let's dive back into the technical weeds to look at how thousands of users physically connect to the storage. Question 5. A customer needs a shared repository for thousands of concurrent users who will be simultaneously editing Office documents. Which architecture is most appropriate?
Concurrent editing.
Yep. Option A, direct attached storage. Option B, storage area network. Option C, network attached storage. Option D, object storage. Now, I have to ask, could you use object storage, option D, if you just built a really good front-end app? It scales infinitely, right?
Well, yes, workarounds exist in the real world, but the exam tests fundamental architectural purposes. Object storage is designed for massive, flat namespaces of immutable data. Backups, streaming media, that kind of thing.
But not live documents.
No, it operates on an eventual consistency model. It doesn't natively handle the real-time byte-level locking you need if two people try to update the same document at the exact same second. You'd get corrupted files or silent overwrites.
Yikes. And direct attached storage, option A.
DAS is isolated to a single server. It fundamentally fails the thousands of users requirement. Option B, a SAN, operates at the raw block level. It doesn't understand files or user permissions natively.
So it has to be C, network attached storage.
Correct. NAS is built for file level sharing. It uses POSS-compliant file locking with protocols like SMB or NFS. The NAS controller natively manages the lock states and directory structures in real time, which is exactly what you need for massive collaboration.
Okay, question 6 is about high-performance protocols. What is the primary architectural advantage of utilizing NVMe over fabrics from modern compute clusters? Option A, it provides massive parallelism and lower latency by bypassing traditional storage stacks. Option B, it allows the reuse of outdated host bus adapters. Option C, it eliminates the need for multipathing software entirely. Option D, it restricts data flow to a single, highly optimized queue.
NVMe over Fabrics is a massive leap forward.
I always hear this analogy that traditional storage protocols are like a single-lane dirt road, whereas NVMe is a 100-lane superhighway.
That is exactly right. The limitation of traditional storage stacks, like SCSI, was the protocol itself. It forces all storage commands into a single queue.
Like option D says.
Okay.
So option D is actually describing the old way.
Exactly. Option D is a trap. It actively contradicts the purpose of modern protocols. SCSI is like a massive supermarket on a Sunday afternoon that only has one single checkout lane open. The flash media can handle millions of IOPS, but the single queue bottlenecks it.
So NVMe provides massive parallelism, opening 64,000 checkout lanes.
Yes, which makes option A the correct answer. It provides parallelism and lower latency by bypassing the traditional stack. It uses remote direct memory access RDMA to talk directly to the flash media without interrupting the host processor constantly.
Nice. And what about B and C?
Also traps. You absolutely cannot reuse outdated HBA's option B because NVMe requires specific high-performance network interface cards. And option C, eliminating multipathing. That's just dangerous. You always need multipathing for high availability no matter the protocol.
Got it. Okay, high-speed protocols are great, but if a ransomware attack hits, that speed just means your data gets encrypted faster. Let's look at protection and efficiency. Question 7. A customer needs to protect their primary HPE storage against ransomware attacks and ensure rapid recovery times. Which solution is most appropriate?
This is critical right now.
Yeah. Option A, unencrypted local snapshots. Option B, synchronous replication to a secondary site. Option C, HPE store once with Catalyst and virtual lock. Option D, an unprotected secondary file server. Now, if I'm synchronously replicating my data, option B, aren't I totally safe? Every write is mirrored instantly.
Oh, that is one of the most fatal architectural mistakes you can make.
Wait, really? Why?
Because synchronous replication perfectly replicates the ransomware instantly.
Oh, wow.
Yeah, ransomware is a mathematically valid storage write. The array doesn't know it's malicious, it's just an instruction to encrypt blocks. So if you use option B, you will flawlessly encrypt your primary and secondary arrays simultaneously.
That is terrifying. Okay, so B is out, and I'm guessing A and D are basically just leaving the front door open.
Pretty much. Unencrypted snapshots option A are routinely deleted by attackers before they even launch the payload, and D, an unprotected file server, is a massive vulnerability.
So that leaves option C.
Yes, HPE store once with Catalyst and virtual lock. It's the correct answer because it's air-gapped and immutable. Catalyst doesn't present itself as a standard network share, so malware scanning for drives won't find it, and the virtual lock establishes cryptographic immutability.
Meaning the data cannot be altered or deleted.
Exactly. Not even by an admin with root credentials until the time retention policy expires. It is mathematically locked.
Incredible. All right, question 8, shrinking data. You are designing an all-flash storage environment for a virtual desktop infrastructure, or VDI, deployment. Which feature is most critical to maximize effective capacity? Option A, post-process deduplication on spinning drives. Option B, inline global deduplication combined with hardware-assisted compression. Option C, thick provisioning of all virtual volumes. Option D, file-level archiving to a lower tier.
VDI is a very unique beast.
Well, yeah, if you think about it, a VDI environment is essentially the exact same Windows OS copied 1,000 times over, right?
You hit the nail on the head. That exact redundancy makes option B the only correct answer. If you have massive redundancies, saving thousands of identical copies of the Windows System 32 directory on premium flash storage is going to drain your IT budget instantly.
Right, but why not just use option A, post-process dedup on cheap spinning drives?
Because VDI workloads have phenomena like boot storms. Imagine 1,000 users logging in at 8 a.m. Post-process on spinning drives would introduce so much latency, the entire business would grind to a halt. It has to be inline, meaning it intercepts the data before it hits the flash media.
Ah, so it hashes the incoming blocks in real time.
Yes, and when it sees those thousands of identical files, it writes exactly one instance to the flash drive and just updates metadata pointers for the rest. That combined with hardware-assisted compression, which doesn't tax the main CPU, is what makes option B correct. Options C and D, thick provisioning and archiving, would just waste massive amounts of expensive capacity or ruin performance.
Okay, that brings us to our final segment, diagnosing the bottlenecks. So you've optimized your protocols, secured your backups, and deduplicated your data. But what happens when the system still slows down? Question 9. A storage array is experiencing severe performance bottlenecks during nightly batch processing, despite having adequate raw capacity available. Which intervention is the most appropriate architectural solution?
Let's hear the options.
Option A, adding additional spinning disk shells. Option B, downgrading the array software to a legacy version. Option C, upgrading the storage controllers. Option D, power cycling the storage fabric, switches. Now, if a system is slow, my first instinct is to buy more disk drives. Why is option A wrong here?
It's the difference between capacity and compute power. The question specifically says the array has adequate raw capacity.
Oh, right.
So adding spinning shells option A doesn't solve the problem because space isn't the bottleneck. Nightly batch processing involves heavy lifting, complex database joins, index rebuilding that requires intense CPU cycles and deep cache reserves on the storage controller.
So the controller is pegged.
Yes. Option C, upgrading the storage controllers, is correct because it provides the CPU and cache needed for heavy I/O. Downgrading software option B is a terrible idea for security and performance. And D, power cycling switches might disrupt traffic but won't fix a controller's CPU bottleneck.
Okay, last question. Question 10. During an infrastructure assessment, you observe that host CPU utilization is spiking and application latency is increasing, but the storage array itself reports minimal load. What is the most likely cause? Option A, the storage enclosures are oversubscribed. Option B, the compute nodes lack sufficient resources to process the storage I/O. Option C, severe congestion on the storage area network. Option D, failing media endurance on the flash drives.
This is a great one. If we connect this to the bigger picture, a storage architect must look beyond the storage array itself.
Right, let's look at the whole path.
Exactly. Because the array reports minimal load, we can immediately eliminate A and D. If the enclosures were oversubscribed or the drives were failing, the array would be screaming about heavy loads or errors.
That makes sense. And what about C, S and congestion?
If the fabric was congested, you'd see latency on the switch ports, but the host CPU wouldn't necessarily be maxed out. It would mostly be sitting there in an I/O wait state, just waiting for packets.
So the fact that the host CPU is spiking means option B is correct.
Yes. The compute nodes lack sufficient resources. The host OS is receiving data from the storage, but it doesn't have the compute cycles available to acknowledge the interrupts and hand the payload to the application. The host server is essentially dropping the data on the floor because it's overwhelmed.
Wow, so you have to go to the virtualization team and say, hey, my storage is fine, your hosts are starving.
Precisely. You have to diagnose the whole ecosystem.
Thank you so much for joining us for this deep dive. Keep exploring the why behind the technology, and we'll catch you next time.